The title of this presentation is Overview and Concluding Remarks on Quantum Key Distribution, Random Matrices, and Error Correction via CSS Codes. To begin with the presentation overview, in the previous two presentations of this series, we've been describing and introducing QKD along with error correction protocols. And specifically, we were considering how are probability measures over error correcting codes obtained, what are the connections with random matrices, and what distinguishes a two-universal QKD hashing protocol from an ordinary QKD hashing protocol. And to answer all these types of questions, we're just demonstrating how probability measures supported over random matrices can be used to introduce and to define parity check matrices, and how these parity check matrices and functions of parity check matrices are used to define different components for ideal, real, and simulator isometries. And obviously, as we've been describing, as transformations which preserve length, the isometries are indispensable for Alice and Bob to be able to determine, beginning from the outputs z sub a and z sub b respectively, how they can transform these outputs to x sub a and x sub b respectively, and then finally to w sub a and w sub b respectively, which each correspond to the shared secret key without which Alice first constructs, and then after which Bob can perform a transformation on to obtain his same copy of the secret key that Alice initially is considering, or is looking to produce and looking to make. And overall, to answer these questions as a starting point, we were referring to a 2021 reference due to Ostrov on quantum key distribution and two universal QKD hashing. And now I wanted to introduce, as a way to close things out, just some more general remarks about the types of arguments and overall methods that we are looking at within this two universal QKD hashing protocol. And then I'll close out this overview part of the last presentation of the series out with some ideas about how error correction comes up in more of an applied sense, more of obviously a much less, significantly less rigorous sense, maybe like how some people maybe look at in terms of making use of quantum algorithms for material science or other very types of more applied computational areas that aren't really proving anything rigorously like how we've been describing. And this is important because whether we're looking at more of an applied or theoretical setting in quantum information theory and quantum information processing, we have to look at and consider functions of the set of anticipated errors, which is to say that we can define functions such that it's taken over a subset S over the field with two elements supported over n qubits given by this mapping, little f sub big S being with a codomain from the base field of two elements supported over n qubits into the set itself of anticipated errors unioned with the abort configuration. And this abort configuration is important because it captures generally the instance in which there could maybe be other types of errors which we could encounter on near-term quantum hardware, or even quantum hardware later down the line if it ever becomes more useful, that could unfortunately result in the two universal QKD hashing protocol aborting. And the value of this map is given by being alpha if and only if alpha belongs to the set of anticipated or likely errors in an abort symbol otherwise. So pretty much, as we've been describing and that we'll reiterate soon, we have to think about robustness in terms of whether a two universal QKD hashing protocol, or even more general, whether a QKD hashing protocol would have to end up aborting, depending upon whether maybe there are some, just aspects of the intermediate outputs to the shared secret key between Alice and Bob that could prove to be problematic for the purposes of unconditional security. And as described previously, we reiterate that we would like to compute objects of the following form. Namely, we're looking at some type of purification state of random matrices. We have this broad term of the first purification term and a ket term of the second purification, in this intermediate product representation to these two purified states, respectively, for the bra and ket, is given by a tensor product representation for the Hermitian complex conjugate of the simulated isometry, the Hermitian complex conjugate of the ideal isometry, and finally just the real isometry itself. And looking at this type of action, it's very important because it's pretty much demonstrating like how I provided for the viewer in various up to constants lower bounds in the security results in the previous presentation of this series, that pretty much we're looking at ways to compare what is the expected or the anticipated difference that we would have from either looking at the action of the simulated isometry on the ideal isometry as well as just the real isometry itself. In a computation that the fidelity also impacts results for the security of the QKD hashing protocol, which is to say that the fidelity between these two states that I described for the view in the previous presentation of this series, the second part, namely looking at the action of the V real isometry with the U simulator isometry upon some purification state, again, some ket for the purification of a random matrix, as well as this ket of Varphy, which is relating to another state that one can obtain from the maximally entangled states that are taken with respect to the Bell basis, has some very similar and very closely related up to constants upper bound to what I had provided in the previous presentation, namely that the power that's appearing in this two factor, it's dependent upon minus k, the number of syndrome measurements, plus n times the total number of qubits, plus or also what's appearing in this term besides the multiplicative factor of the n is the hashing function evaluated at little r over n, which is the total number of qubits r, little r, at which there can be bit flips and phase flip errors, which is normalized in the total number of qubits from the initial state that Eve is distributing to Alice and Bob in the two universal QKD hashing protocol. And however, this kind of mysterious looking plus 5 minus 3 halves is coming into play because when we were talking about and describing computations with real with simulator real and ideal simulator ideal and real isometries in the previous presentation of the series, we were really drawing attention to the viewer to the fact that to make functions more efficient for functions of parity check matrices, we were looking at introducing multiple terms rather than idealizing everything down to a single quantum state or a single ket value in comparison to the in comparison to the simulator ideal and the real isometries that were first defined and introduced in Hofstra's work. And the fidelity as a L1 norm, it's given by this definition. And in the first presentation of this series, I had reproduced a couple of key terms that were associated with quantum key distribution and two universality and QKD hashing from Oster's paper, which were relating to block size, output size, key rate, security level, and robustness. And all these terms, they're pretty informative to keep as kind of more general buzzwords, or I guess one could call it that, or just really just ways in which someone could be able to have some more general type of impression in mind in terms of what are the actual components of quantum key distribution, because you're starting with a block size, which is determining from a total population of qubits, how many qubits would Alice and Bob want to be able to reliably transcript to be able to construct some shared quantum secret key between them, which is obviously proportional to and it's related to the output size that they're going to see because they want to actually maybe maximize the number of qubits that overlap in the shared quantum key that Alice first constructs that then she gives to Bob that then he performs a transformation on to obtain his secret key. And the key rate is relating to the fact that we're trying to quantify what is the probability that if they make some shared secret key between them, there could maybe very optimistically being some unconditional security guarantee, namely that no matter how much computational power Eve has, despite the fact that she distributes initially in the two universal QKD hashing protocol a little n qubit state to Alice and Bob, that really she would never be able to determine what are any of the constituents or any of the qubits which are comprising or which are making up this shared secret key which Alice is first constructing. And the security level, like we've been describing, is in theorem two from the previous presentations that we've been describing. And it's just related to the fact that the higher the security level, the higher the probability that Eve could actually maybe in some future instance or some future use of the two universal QKD hashing protocol be able to determine what are basically the constituents in the individual qubits or other parts of the shared quantum secret key between Alice and Bob. And finally, robustness again is relating to whether the two universal QKD hashing protocol would end up aborting often or not. And obviously, we would, from an algorithmic sense, if we're looking to draw some quantum key at random from the quantum key distribution, we wouldn't want the protocol to actually compile all the way through or actually output some hopefully desired secret key between Alice and Bob if Eve could actually intercept it and determine its contents. So we would, in that case, we would really prefer for the two universal QKD hashing protocol to abort. And when we were describing things in the first presentation and finishing up that part of the series, we were introducing a few objects from the first reference, which is relating again to the fact that it's great to reiterate the following decomposition, which is involving a classical transcript of communication between Alice and Bob, which was introduced earlier in the first presentation of this series in terms of the abort states of the QKD hashing protocol, which is to say that this reduced density state twiddle row of WAWBCE, where C in this subscript to this reduced density state denotes the classical transcript of communication that Alice and Bob used to construct and to make their secret key, which is can be identically decomposed as an outer product in terms of the abort configuration that Alice and Bob abort the two universal QKD hashing protocol with respect to the space of secret keys WA and WE, WA and WB, with a tensor product of the reduced density state from the classical transcript with Eve from supported over the classical transcript that Eve has and that she's gathering from the attempts of Alice and Bob to make their secret key that she also aborts, whereas this remaining term, which is appearing in the decomposition, is a summation over all instances of the quantum secret keys which are distributed between Alice and Bob, little w sub a and little w sub b, and we're having a very similar expression, namely a tensor product with a reduced density with support of CE, namely the support of the classical transcript from Eve, which is a function of little w sub a and w sub b, and the term which is preceding this reduced density operator for Eve when she doesn't end up aborting the two universal QKD hashing protocol is dependent upon an outer product over the same space of secret keys W sub A and W sub B, with little w sub A and W sub B appearing in each one of the parts of this outer product. And the probabilistic collision bounds are relating to the fact that from definition 4 of Oster's paper, he denotes a family of functions boldface H, which can be expressed in terms of a mapping from one finite set boldface X to another finite set boldface Y, with the two universal collision probability from the family of hashing functions satisfying for some strictly positive epsilon, the probability of sampling a hashing function over the family of all such hashing functions such that h of x is equal to h of x prime is less than or equal to epsilon. But before further delving into QKD, we introduced some basic notation which the viewer can recall, which was to say that rho of ABE is the state encoded by Alice respect to Bob, which is the n-qubit state that's initially transmitted to them by Eve at the beginning of the two universal QKD hashing protocol. And also, like we've been describing in the decomposition for the reduced density state of twiddle rho of WAWBCE, just without taking the reduced density state, just rho of WAWACE denotes the state that Alice and Bob share for the quantum secret key, with C denoting a transcript of the classical communication between them that they use to make and to construct their shared secret key, which is drawn uniformly at random from the quantum key distribution. And to further go back to some parts and components that we had described in the first presentation, we were looking at making significant use of the projection operator over the polygroup of n qubits, which is given by P where P is a function of this vec G, where vec G is an element of the polygroup supported over n qubits, as well as X. Just it's oftentimes taken to be just a rational parameter, or other types of parameters U and V for vectors. And it's given by being expressed in terms of 2 to the minus n, which is like 2 to the minus number of qubits, which appears quite often, as well as a product over over j between 1 and m of the identity operator plus minus 1 times x to the j, g to the j. And the action of the polygroup on two elements, zooming out a little more further from this previous expression that's given from the projection operator, is given by the fact that straightforwardly the action associated with the multiplication operation of Gn for some Gg prime in Gn satisfies Gg prime is equal to the minus 1 times this this power, which is dependent upon the group homomorphism G prime G, where this group homomorphism that's appearing in this exponent script f is given by a mapping from the polygroup into the space of columns, or sorry, of rows, where each one of the rows of this 1 by 2n finite dimensional representation is taken over the base field with two elements. And component wise, if I give you one element of the polygroup, omega sigma u of 1, sigma u of 3, it maps into u and v, where again, sigma 1, sigma 2, sigma 3 are the base of the traceless 2 by 2 matrices, which appear all throughout quantum physics and quantum mechanics and quantum information theory. In this strictly n, this little n parameter being strictly positive, it's relating to the number of qubits, as well as this script s term being having the block matrix, the following block matrix decomposition along the anti-diagonal. And so the statement of the lemma is related to the fact that we're looking to obtain approximations for outer products of maximally entangled states through Bell basis elements, which is saying that we're fixing some little n number of qubits corresponding to the number of qubits that in the state that Eve initially transmits to Alice and Bob, as well as these two elements, alpha and beta, over the base field with two elements. And it's just providing, like we've been describing, just basically a generalization of a maximally integraled outer product that was provided in the first work in the reference from 2021 that we've been discussing throughout this series, and how it relates to just pretty much embedding outer products within each other and being able to perform error correction like how we described in the second expression, the second equality for the outer product. We're looking at a Hadamard operation, which is determining the number of phase flip errors, whereas the first expression from this decomposition of this embedded outer product, we don't have any Hadamard operation. So, which is to say that we're looking at the occurrence of bit flip errors in this first expression, this first decomposition for a maximally entangled outer product. In the statement of the security result, like I said, it's really great to continue reiterating this type of result because it's just further demonstrating how this outer product decomposition, which I had provided in the previous slide, it's relating to the security result because we're just pretty much taking a square root of in these computations to finish in the proof for the security result for this novel two universal QKD hashing protocol pi prime. We're looking at this constant C, which I described for the viewer in the previous presentation of this series, the second part, which is dependent upon this additional factor of log base 2 squared of C plus this 5 halves times 5 minus 3 over 2 factor, as well as this other term, which is appearing as a common term, namely the hashing function, the number of syndrome measurements, the total number of qubits, and little r, which is determining the total number of bit flip and phase flip errors. However, besides applications to QKD, several computational routines stand to significantly benefit from further theoretical research on error correcting codes, which is important because overall, a lot of people in industry now, whether it's maybe in quantum computing or biotechnology or other types of related areas, they may not necessarily be as interested or as enthusiastic as we are, as I am, and a lot of my viewers are, in terms of the theoretical prospects of this research. So I just wanted to end up the overview part of this presentation of the series by describing a few presentations, other presentations across the channel that I've given, as well as connections and potential applications in the near term with QKD. And this is relating to previous works in quantum physics because I've described and looked at a wide variety of computational methods and different types of ways to try to connect theory and experiment. And probably the most applied thing that I first did was this middle paper, Variational Quantum Algorithm for Measurement Extraction, in which pretty much I wrote up code using Google Quantum's AI Circ package, as well as interfacing that with different types of simulators for state vectors, being able to approximate solutions to around 15 partial differential equations. And then more moving towards more the theoretical side, I looked at optimal and approximately optimal quantum strategies for XOR star and FFL games. And then this year, I described and looked at further quantum strategies, error bounds, optimality, and duality gaps for a wide variety of multiplayer settings. And then most recently, or one of the more recent papers also was relating to the distribution of classical states over potentially noisy quantum channels, which was relating to the bit transmission rate, as well as obviously to error correction, authentication, and false acceptance probabilities. And again, towards more of this applied side of making use of quantum key distribution for the purposes of improving the fidelity of quantum computation, there are many bioinformatics algorithms and pipelines which share connection with molecular docking workflows, which is very much of interest for a lot of people in industry because they're looking at making use of quantum chemistry, electronic structure calculations, which is relating to structure prediction, in which one of my videos I talked about approximating binding affinity of cell-tog DB compounds, also even determining whether there are any uncertainties or probabilities of errors with sequencing, which is relating to visualizing de novo assembly graphs with bandage, which is more generally relating to de novo graph assembly, even reverse translation of amino acids, which can help us determine what are the overall process in which just basically the genome is able to disseminate and produce its material throughout some model organism. And this can also be related to being able to determine whether there are any types of novel assays in the sense of synthetic biology for that we can use for the purposes of cell annotation and even for transcriptome assembly. And together with these PDB-QT files, which is a very common type of format that even people who make use of quantum chemistry and electronic structure calculations use, in another previous presentation that I've been describing for the view in a previous slide, I was looking at making use of a structure, a possible structure for the COVID-19 receptor and being able to apply some type of just basically classical version of electronic structure computations, which would then allow us to determine what would be the types of maybe novel therapeutics which could really stand to benefit from error correction protocols within the context of quantum key distribution that I've been talking about and highlighting for the viewer in this series. And now I'm going to just also provide a little bit more detail from when I was a master's student in the lab and I had done some initial work from that middle paper that I described from my previous works on quantum physics, which is relating to variational quantum algorithms that I talked about in a few APS March and April meetings, as well as a remote seminar at the Dartmouth Applied and Computational Mathematics seminar, which was relating to the fact that I was describing a variational quantum algorithm due to Labache et al. If I remember the title correctly, is Variational Quantum Algorithms, I think, for Nonlinear Problems. And I was describing the ansatz that we use, as well as the applications of the quantum algorithms for solving other PDEs. But overall, how unfortunately this was a very naive type of way to do things because it was relying on a noiseless quantum simulation. Because even though Circ from Google Quantum AI, it does have logical operations which can be able to generate noise, are the fidelity of our results and the reliability of our results from the quantum computation that we were able to perform, it was really almost completely ruined and completely destroyed as more noise was added in. So pretty much that's why robustness and noise and error correction is very important even for more of these applied settings. And this is important because this is just a slide that I reproduced from some previous presentations I've given, in which we're interested in a variational quantum algorithm and generalizations of the variational quantum eigensolver in terms of initializing and variationally modifying parameters for generating solutions to other PDE initial value problems. Which is to say that one of the when I was giving this presentation in the March APS April meeting, I think a few years ago at this point, I was describing how we can look at the nonlinearity space of nine PDEs, whether it range from Navier-Stokes, Maxwell, Boostnext type, Lencian, Camasso-Holm, DSW, Hunter-Saxton, Benny-Luke, with the requirements for the ansatz that we're trying to configure this time evolution in this simulation in a very favorable position within Hilbert space, which could potentially impact the initial conditions on the first and higher order derivatives of the solution state. And after being able to formulate and brainstorm the types of nonlinearities that would be interesting for us to explore, we can formulate a cost function in which we pass to this middle component of this workflow relating to the cost function ground state space, in which we pretty much transform the equation into adder and adder dagger operators, which allows us to form a resulting quantum superposition for solution state approximation. And finally, the good friends of ours at Google, their package from Google Quantum AI comes into play because we're making use of Circ, which is allowing us to automate quantum circuits and also evaluate them to be able to extract some measurements and assemble some solution approximations. And the optimizer pool that we have is relating to infill and snotfit, the Nevergrad open source optimizer from Facebook Research, which this Nevergrad optimizer was extremely helpful for being able to perform these proof of concept noiseless quantum simulations. And there are even other types of open source optimizers, including particle swarm, competitive particle swarm, covariance matrix adaptation neighbor algorithm, or VDCMA, another variant of the covariance matrix adaptation optimizer, as well as even a gradient-based optimizer with sequential least squares. And for Navier-Stokes equations, which was one of the earlier equations I was interested in looking at, I was trying to simplify this cost function by just looking at Couette flow, because a lot of the turbulence and a lot of the other nonlinear terms which make Navier-Stokes such a difficult partial differential equation to solve, and even obviously relating to the $1 million problem on uniqueness or on or on existence of such solutions to Navier-Stokes. It was really helpful because, as you can see from this figure that I've reproduced from a 2018 reference, as well as other types of demonstrations, there can be some types of very very computationally not very computationally costly solution curves, which can generate, which can reflect upon different aspects of the flow and how turbulence and eddies and other types of interference patterns can form in the liquid, which would presumably be governed by the Navier-Stokes equations, as well as the density of the liquids that these particles and these other, the solutions to this partial differential equation are propagating within. And related to the Navier-Stokes equations was the Camasso-Holm PDE, which was a really great partial differential equation to consider from a reference that I was looking at from 2005, because is able to provide just basically several types of example solutions of interference patterns, which was helpful to consider when I was making significant use of the Nevergrad optimizer to approximate solutions to the Camasso-Holm PDE with noiseless quantum simulations. And the physical significance of solutions is related to the fact that there can be a wide variety, so many possible interference patterns, which can appear, namely maybe smooth periodic or smooth with decay or peak-on with decay, in which maybe at this point, this peak, the derivative of the solution would become close to being undefined, or would itself become undefined, because the profile for the wave propagation is having a cusp, and as well as many other types of amalgamations and combinations through composite waves, depending upon different choices of parameters. A measurement extraction without noise that was able to extract from the Camasso-Holm partial differential equation, which was relating to the fact that you can look at different types of optimizers which vary step sizes. And even though I did experiment and try in different types of step sizes, it's mostly all the same in terms of actually the solution approximation that was generated without noise. However, we can see that the PD solution approximation asymptotes near negative infinity, corresponding to some global minima of the profile that's being generated, and also, however, closer to the middle of the period of the motion, readout from the quantum states corresponding to the PD solution continues to fluctuate. So it's important that the partial differential equation solution that this generalization of the variational quantum eigensolver is able to generate is able to determine what are the sources of fluctuation throughout different periods of motion. And overall, for PDs with more complicated nonlinearities, varying the time step of the stochastic or the deterministic optimizer does not alter the resolution or what is the actual value of the extracted measurement without noise. So concluding remarks is that we described several aspects of two universal QKD hashing protocols, including, again, like we've been describing and reiterating, probability measures supported over random matrices, parity check matrices for marginals of probability measures supported over random matrices, as well as expansions for maximally entangled outer products, which has implications like I've been describing in closing out in this overview part of the presentation of the series, implications for numerical simulations as appearing in generalizations of the variational quantum eigensolver, and further research directions on determining whether error correcting protocols can continue to remain resilient with other QKD hashing protocols is of interest to further explore. And thanks for watching.